And so without any further delay, I will start the presentation on the thesis that is titled Multiscale Simulation of Wildfire Spotting, in French, Modélisation multi-échelle des sautes de feu. So the agenda for today is that I will first provide a short introduction to wildfires and actual spotting. We will have some context and motivation of the thesis and what are the main objectives that are covered during this thesis. Then we will really dive into the work that has been conducted as part of this thesis, and we will have, of course, some time for summary and perspective, and of course, some questions. All right, so wildland fires, as you may know, has negative consequences both on humans and ecosystems. When we talk about humans, we mainly talk about the impacts on health, so mainly related to human losses, but also impacts on mental health, different kinds of air pollution that lead to breathing problems, and also, of course, the impacts on infrastructures that lead to economic losses in our societies. Regarding the ecosystems, there's as well losses in terms of animals and vegetation. It is estimated that, for example, during the Black Summer events, there was almost 3 billion animals that were displaced due to the fires. In the case of the animals and vegetation, they have developed actual strategies to fight or to resist to fire regimes. It's the case, for example, for vegetation that have developed thick bark, for example, pine, resprouting strategies, but also selecting it to disperse seeds when there is a fire event. In all cases, the future doesn't seem very bright. The climatic conditions, in this case for Europe, they show that there is going to be a lengthening of the fire season. Yep. This is Is it disturbing or? All right. So there's going to be a lengthening of the fire season, particularly in Europe, actually in the Mediterranean region, where we expect to have 10 days of supplementary fire season, so days where fire is likely to occur in the next 30 years, and almost a whole month, so 20 days, in the next 50 years. So to try to cope with this situation, one thing that we can do is to actually better understand the propagation of fire. Usually the physics of fire propagation are summarized in this kind of diagrams, where we have the flaming and the active fire front, which is preheating the unburned field. Some pyrolysis gases are released, and of course the flame spreads towards the unburned field. And so to model this kind of propagation, we usually use what is called rate of spread models, which are giving us the velocity of the fire front as a function of the wind, so the atmospheric wind, the slope at which the fire is propagating, and also the few characteristics such as its slope and its humidity. One of the things that is missing in this kind of models, and I will talk later about it, but is the propagation of fire due to fire ants. So fire ants are small pieces of vegetation that you can see here. They are coming from bark or from twigs and branches. And actually these pieces of vegetation, they can be detached during a wildfire event. They can be transported by the wind. And once they land on the fuel bed, they may reignite secondary fires known as spot fires. This whole phenomena describing the generation, the transport, and the ignition of secondary spot fires is known as wildfire spotting. It's actually quite a complex problem because different types of fuel will generate different amounts of fire ants in different sizes and different shapes as well. Fire is also an important variable in this problem. The more intense the fire is, the more likely it is that we have more fire ants. The atmosphere also plays an important role, particularly when we have a well-developed convective column. It is more likely that we get what is called long-range spotting. And finally, topography is also going to play a role into this phenomenon. We usually we tend to describe spotting in different distances. So firstly, what is called short distance, that's everything that is going, that is creating secondary spot fires at a distance of 500 to 700 meters from the fire front. We usually see a large amount of small fire ants that are traveling with the wind. And in some cases, it can become a very intense phenomenon where there is thousands of small fire ants traveling with the wind in what is called an ember shower or an ember storm. And in this kind of situations, it's quite dangerous because there's a large amount of firebrand that can get trapped and lead to urban fires. Then we can move to what is called medium and long range or long distance spotting. In this case, it's when the spot fires are created further than 1 kilometer from the main fire front. So what you see here is a video of a wildfire in California with a very well-developed convective column. And at some point, the camera will zoom in, and you will see smoke coming out of the ground. So these are spot ignitions coming from the fire brand. You see that the fire front is around here, so this is a distance of around 7 to 10 kilometers. So in this case, there's a few or single fire brands that are going to ignite secondary spot fires that travel for several kilometers. And if we want to model this kind of phenomenon, the characteristic length is around 100 meters. And so this, as I said at the beginning, this spotting phenomena is starting to get represented actually in couple fire atmosphere modeling, but when we started the thesis, it was not really something that was included in these frameworks. And so couple fire atmosphere models are frameworks that represent both the propagation of the fire and also the perturbation of the atmosphere due to this fire propagation. So usually the way it is coupled is that there is a fire propagation model that is describing the advancement of the fire front, and it's releasing heat flux and vapor flux to what is called an atmospheric model. As a result of this perturbation, the wind changes, there are wind changes captured by the model that can be then used as an input for the fire propagation model. These models have shown actually quite good results, and you see here, for example, one wildfire in Corsica. And you see here the picture, so they describe quite well the interaction between the fire and the atmosphere. And so the main motivations of this thesis are mainly summarized here. So we have just said that the spotting is something that complicates wildfire control strategies because we can have secondary spot fires far ahead of the main fire front. It's actually one of the main causes of habitat loss during wildfires, and is or was a missing process in couple fire atmosphere models. And so these couple fire atmosphere models are a framework to actually resolve weather and the fire coupling. And the idea is that they will develop to learn more about the interaction between fire and atmosphere, but also to provide results faster than real time, meaning that we're kind of forecasting the fire propagation. And so the final piece of context that this PhD was part of a joint PhD between the CNRS and the University of Melbourne, named Multiscale Experimentation and Simulation of Wildfire Spotting, and that was conducted at 2 fire-prone regions, Australia and Corsica, mixing experimental and numerical approaches. And so the problem that we are trying to tackle with this thesis is to actually find the potential spotting areas faster than the real-time formation. So meaning that we're trying to forecast where spotting is likely to occur. So the main objective of this is to actually implement the spotting into a couple fire atmosphere model. The 3 objectives, the sub-objectives are firstly to analyze and compare the current and existing fire brand models. We will then propose a reduced fire brand transport model. And finally, we will implement the numerical method to include spotting into couple fire atmosphere models. Alright, so moving to the first part, I will shortly present the work that has been done to analyze and compare the different existing fire brand models. So it is since the 60s that we know that we're able to actually obtain the first simplified trajectories of fire brands, and more recently with the usage of CFD and LES techniques, coupled with what is called Lagrangian models, meaning that they describe the trajectory of fire brands, that we have learned more about the turbulence and the impact of vertical terminal velocity on these kind of trajectories. However, there was still a missing gap regarding the influence of drag and combustion models on the final trajectory of fire brands. So what we have done for this part is that we have used Meson H4 which is a couple fire atmosphere model, to obtain realistic wind flows that describe a realistic wildfire plume. Once we have obtained this wind flow, we're able to calculate the fire brand trajectories in this computed 3D flow. And to do so, we will assume that fire brands are point mass particles with 2 different cylinders, so mainly that they describe they influence the aerodynamics of the fire brand. And so the ones that we chose were cylinders and disk, and we will compute the 3 translations of the fire brands. These particles are subject to different initial conditions, such as the size, its density of the material, and also the positional velocity. And the main thing that the main metric that we're going to use to compare the different models is actually the ground landing distributions of the firemen that have landed on the ground. So you see here an example of a fire plume that we use to then calculate the trajectories of the fire. So in this part we use different models that have been used already in the literature. So I just summarized the titles of the papers, and also the combustion models. So these models will give us a reduction of the size, or the density sometimes, of the fire. So once we have these two models that describe the aerodynamics and also the combustion, we're able to then calculate the trajectory of the fire. When we first look at the results without combustion, so meaning that we are just trying to understand the influence of the aerodynamic coefficients, we see actually, I'll just summarize two examples, but this is an example of the firings that have landed for cylinders, and this is for disk. And we observed that actually all the cylinders were traveling consistently shorter distances than the disk. So this was something that was already known, but we have also verified using a more realistic wildfire plume. When we now take into account the combustion, we observed that for cylinders we were consistently having a short range behavior, meaning that all simulated firings were traveling less than 500 meters. So here I only show a disk, and we see that there is a large variability between the obtained results using two different combinations of models. In all cases, we observed that the disks were traveling longer distances than the cylinders. So when we try to understand what is going on, we can plot, for example, the longitudinal travel distance of the firings as a function of its initial properties, such as the density, the thickness, and also the radius. And what we observe is this kind of bimodal distributions, where firings are either traveling long distance or short distances. So mainly what we observe is that the trajectories are going to depend on the firing inertia, which is something that indicates us how much the firing is going to resist to changes in the wind flow, and also at which time scales. And it also depends on the wind flow. So meaning if the firings are caught within an updraft, they will be lifted far away, and then turbulence is going to spread them both horizontally and vertically. In this animation we show what I have just seen, what I have just said, sorry. So here we see that the firings are caught in the updraft, and they're going to travel longer distances. Otherwise they will just travel with the wind, and most of the firings are traveling are traveling short distances actually. So we concluded that the firings were best calculated using this combination of aerodynamic and combustion models. It is, however, quite time-consuming, because these kind of simulations, they take around 10 hours to simulate around 60,000 firings. And as part of the outcomes of this first part, we have developed an open source library that compares all the existing models, and this was published in the Fire Safety Journal some months ago. So moving to the second part, where we try to propose a reduced fireman transport model. We have just seen that the 3 degrees of freedom fireman's trajectory simulation, they require a very small time step to actually solve the momentum and to have a stable numerical scheme. There's also, it's quite sometimes problematic, because we need to have a comprehensive selection of the aerodynamic and the combustion models to calculate the trajectories. So what we propose is to have a different formulation of the fireman transport, and to do so we're going to use a similar approach. So we're going to compare the previous complex model that described the aerodynamic and the combustion of the firings to a new reduced model that I will just present now. We're going to use Meso-NH for fire to obtain realistic wind flows, and we're going to do so across 2 different topographies, a flat terrain and a hill terrain that you see here. In this case, what we see is that there are differences in terms of the wind flow and the plume shape as well. You see that in the case of the flat, it is reaching higher altitudes, and particularly the wind at the ground level is quite different across the 2 different simulations and topographies. So the model that we propose is that instead of calculating the actual accelerations of the fibrant, we're going to just calculate the velocities. So this is with the idea of relaxing the constraint on the momentum and to be able to increase the time step during the calculation of the trajectories. So the idea is to relate the horizontal components of the fibrant velocity to the horizontal components of the wind flow, plus a turbulent contribution that is actually updated every tau over 10 seconds, where tau is the characteristic time of the fibrant. This is indicating us how much time the fibrant is going to take to adapt to the local wind flow conditions. And finally, the vertical component of the fibrant is the vertical velocity of the wind flow minus the terminal velocity, which depends on its density and different variables that were adjusted to the model. And so, of course, we're able to calculate the trajectory, but we need to also to describe for how long we're going to calculate the trajectory, and so this is given by a maximum time of life that is provided using experimental data. So here I show the results for the flat terrain and the hill terrain. In orange you see the complex model, so the one that describes the aerodynamic and the combustion. And in gray lines you see the reduced model, so the one that I have just presented now. What we see is that the reduced model is able to reproduce the similar shapes compared to the complex model. It also reproduces well the longitudinal travel distance and also the horizontal spread. In the case of the hill terrain, we see that there is kind of a deflection to the right in this part here, and we observe that the reduced model is also able to describe this deflection to the right, which is likely due to an interaction between the plume and the topography. We observe that the reduced model produces similar longitudinal travel distances and a similar horizontal spread. And when we calculate the score skills, we can observe that we can deduce that the model is matching the complex model at scales of around 200 meters. So when we take into account that the travel distances are around 10 to 15 kilometers, this is quite acceptable. And the very interesting part for us is that we have increased the time step from 0.01 second to a single second, so that is, of course, more computationally efficient. And so here I just show again visualization of the fibrant trajectories, and you see that in the case of the reduced model here in pink, it is matching the same kind of behavior as the complex model, where some fibrants are caught in the updraft and they are transported farther downwind. So of course, we still need to find a way to estimate the fibrant's time of life, so how long we're going to calculate the fibrant's trajectory. And making use of the fact that I was in Australia last year, we tried to perform an experiment on Eucalyptus obliqua, which is a species that is well known for its spotting potential. It's very common in southern eastern Australia, and there was a knowledge gap regarding the large size fibrants. So meaning that the small ones were studied, but the long length fibrants were not really studied. It is a tree that has a very fibrous and detachable bark. It is vertically arranged, so the flame can also creep up very easily and create a lot of different fibrants. So what we did in this experiment is to actually manufacture fibrants in 3 different sizes, using 10, 15, and 20 centimeters length. We will then dry them in the oven at 105 degrees for 24 hours, and once they were dried, we will ignite them at one end, as you see here, so meaning that just the tip of the fibrant is ignited, or across the whole surface, as you see here in these 2 fibrants. And the ignition time is adjusted related to the mass of the fibrant. Once the ignition time has been completed, we will then introduce them into the wind tunnel, and once it is in the wind tunnel, we can then measure the combustion times and also the mass at burnout. You see here one of the fibrants that is within the vertical wind tunnel, so the wind flow is coming from the bottom to the top of the section. And so when we do this for all the different sizes and the 2 ignition methods, we obtain this kind of results. We see that, for example, the flame out time, so the time during which a fibrant is flaming, is actually not really dependent neither on the size nor on the ignition method, which was quite surprising as well. And what we observe is that the mass ratio, meaning that the final mass over the initial mass of the fibrant, does seem to depend on the ignition method. So, for example, the whole surface fibrants are more fragile because we recover less mass at the end of the experiment. So we were able to obtain different combustion times for different types of fibrant, One of the maximum combustion times, so meaning flaming and smoldering, that we measured was around 440 seconds, which is comparable to previous experiments that were performed using this kind of facilities. We observed an interesting phenomenon, which is named reflaming. So here you see that so in this case the wind is coming from the bottom towards the camera, towards us. There is one fibrant that is spinning, that is not really flaming, and at some point it will reach horizontal equilibrium. There is some smoke that is starting to be released, and in a few seconds we will see that there is that we will see a flaming that is getting attached to the fiber right now. So this was also quite nice to observe. We observed it for almost 25% of the samples, and it's of course increasing the overall hazard and probability of ignition if these kind of fibrants land on a receptive fuel bed. So as part of this second part, we have several outcomes. So we have studied eucalyptus oblique fibrants that seem to have a maximum combustion time, because the ones that we measured were comparable to the ones that had already been measured. But we can conclude that they are not really likely to spot at very long ranges, meaning distances greater than 10 kilometers. So this is actually accepted for publication and should be published very soon, I hope. And there is also an outcome of the reduced model that we have seen that it reproduces the similar ground landing distributions when we compare it to a complex model. We have a numerical scheme that is stable with a time step of 1 second, so that is 100 times greater than the previous one. And of course that is based on this kind of experimental data. And so this was published some months ago as well at the International Journal of Wildland Fire. So right now I will move to the third part, where we describe the spotting parameterization into a coupled fire atmosphere framework. So the approach that we're going to follow in this part is very similar to the previous one. So first we're going to test the new method on a set of idealized situations, and then we will apply it to a real case scenario. The method that we propose is to actually have what is called a Eulerian formulation that calculates the transport of a fibrant mass scalar field, meaning that instead of calculating thousands of individual trajectories of fibrant, as we see here, and as we have calculated in past, we will rather just calculate the transport of a single mass scalar field. The way that we have parameterized this in MESO-NH for fire is to inject constant fibrant max flux that depends on the fuel classes. So for example, for the true fuels, the mass that we're going to inject into the atmosphere is 1 kilogram per meter squared per second. And for the grass fuels is 0 kilograms per meter squared per second. So we make the assumption that grass fuels are not likely to produce fiber material that can travel for very long distances. And to compute the transport of this scalar field, we're going to use what is called a diffusion advection equation that you see here. And we will force the scalar field to fall at a terminal velocity that is provided here. That depends as well on the density that we have chosen and parameterized for this particular case. So just to show what it looks like, so here we have an idealized case. In gray you see the smoke from the fire, in pink you see the Eulerian field, and in green you see the Lagrangian results, so the individual calculation of fibrants. So I just show it another time. We see that the smoke is just advected with the wind. The pink field is falling just at the same rate as the individual trajectories. And so we're going to calculate this configuration in the same way that we have done before. So for a flat and a hill terrain. And what we observe is that for the hill terrain, in black gray lines I'm showing the Eulerian formulation, the Eulerian results. We observe that the Eulerian model is able to provide a similar shape when compared to the Lagrangian model. Of course, we miss a lot of fine details, but the longitudinal travel distance is similar, and the horizontal spread is also very comparable to the actual Lagrangian model. When we take a look at the hill terrain, we observed that the area model is also reproducing this kind of dynamic where the longitudinal distance is increased, and you cannot see here, but the horizontal displacement is also matching the one from the Lagrangian particles. So again, when we calculate the score skills for these simulations, we observe that the Eulerian formulation is matching the Lagrangian simulation at scales of 200 to 400 meters, which is very acceptable, knowing that the travel distance is around 15 kilometers. And so now moving to the applied case, we were going to use this parametrization into the Mount Bolton wildfire that happened near Ballarat, so not too far away from Melbourne in Australia. It's an interesting case because it was a very short, both in space and time, wildfire that show actually what is called extreme fire behavior with tree torching, tree crowning, and of course, spot fires. We were lucky enough that the CFA, or the Fire Agency of Victoria, was able to report where and when the spot fires were happening. So we know more or less exactly where the spot fires were reported and also at which time steps. And finally, the interesting part as well is that there was a mobile radar that was deployed on the field and that was scanning the plume from behind, so we can also get some information related to the dynamics of the plume. So we're going to try to reproduce this case using Bessagnet for fire. In this case, we will have 3 different domains that are nested, sorry. The first one is running at 2,000 meters of horizontal resolution. The next one is at 400, and finally the small one where the fire is coupled is at 80 meters of horizontal resolution. Just for comparison, Melbourne is around here. And so what I will show you right now is the observations in blue and the simulation in red of the actual fire propagation during the event. So the fire is starting here. We see that at the beginning the simulation is not really matching the same kind of behavior. Actually, the observations are spreading quite fast at the beginning. This is likely due to the spot fires that you see here in yellow. And at some point right now, there is a wind shift, so the fire front is propagating towards the east. And there's more spot fires reported here, and a final one that occurred at a distance of around 6 kilometers that was reported here. So in our case, the simulation is not really matching, is lagging a little bit behind the observations, but we observed that the dynamics are well reproduced, meaning that the simulation is firstly spreading towards the south, and then towards the east as the wind changes. This is maybe a little bit difficult to understand, but here I'm showing the results from the simulation. And on the bottom part, the radar observations that were obtained by the mobile radar. So this is the location of the scanner, the radar I have just shown. In pink, we have the ISO volumes of the fire and mass scalar field. And this is a slide showing the concentration of mass scalar field in a log scale, actually. So we see that there is this first convective episode. We still don't have any data related to the radar, but it will come in a bit. You see that also how far the fire and mass scalar field is being transported. And in a bit we will have the radar, I hope. In any case, we observed that the spot, the fire and mass scalar field there was a first convective episode, and there is a second convective episode as well. In the simulation, we can observe as well the liquid water content that is well reproduced by the simulation. And right now, so this is, for example, some rain that is coming. We see that the observed plume with the radar was reaching altitudes of 5,000 to 6,000 meters. And actually, when you compare the two visualizations, you observe that the structures are moving at the same speed, meaning that the dynamics of the atmosphere are well captured. As well, the simulated plume was also reaching similar heights of around 5,000 meters. So this is just the same slices that I have shown before, but at 2 different time steps. And we see that overall here in the bottom part is the simulation, this is the radar observations, and we see that the height of the plume is well captured, and also that the model is able to reproduce, for example, the rain or the liquid water that is observed by the radar. So now that we are confident about the evolution of the fire front, but also of the description of the simulated fire plume, we can take a look at the ground landing densities of fire brand. And so in this part of graphs, I will show accumulated fire brand mass during 30 minutes, so from the beginning of the fire until the next 30 minutes, on a scale from 10 kilograms to 0.01 kilograms. So we see that at the beginning, for the first 30 minutes, there is some predicted fire brand mass that is falling towards the south. Then we have this intense episode, a convective episode, where the travel distance is increased. We start to see the shift into the east of the wind and also the fire. We see as well the second convective episode, where the travel distance of the fire brands is increased, of course. Then we observe the first spot fires, here in red. We observe as well a decrease in the travel distance of the fire brands. There is a third convective episode here, where the travel distance is increased, and more spot fires are reported in this part here. They're still lagging in the predicted fire brand landing density, so that is quite good for us. Some more spot fires that are reported here, and a general reduction in the travel distances of the fire brands. This is, I think, the last one, where we see an increase as well in the travel distances of potential fire brands, the final spot fires, and the final spot fire that was reported here during the event. So in this way we have accumulated results for 30 minutes, but we can also try to visualize it more dynamically. So in this video I'm showing the densities here in pink of fire brand mass scalar field in a log scale, so it's not the same as before. We see that at the beginning we have this intense convective episode that is increasing the travel distances of fire brands towards the south. In a few seconds the distance will decrease. So as you see here, the field is coming back towards the fire. Then we observe the wind shift, where fire brands are going to start to be deposited towards the east a little bit. We see more spot fires that are being declared here in yellow. So right now there is as well a large predicted spotting area that will decrease again. We observe this second kind of arm, and we observe actually this very funny spot of pocket of fire brand density. And in a few seconds as well, we will see that there was a reported spot fire in the same place as it was predicted by the model. So, of course, we have to be careful about the interpreting what the model is telling us, but at least from this kind of simulation, we observe that the model is making sense and provides quite useful information about the temporal and also spatial dynamics of fire brands. The very interesting part, of course, is that this kind of modeling is executed online, so at the same time as the coupled fire atmosphere simulation. It only takes 2 hours to have a full 8-hour forecast of the fire propagation. That is identifying the potential spotting areas. And maybe more interesting as well is that it also is telling us the densities of the spotting. So it is telling us where spotting is more likely to occur. So as a short summary, during this thesis we have compared the existing aerodynamic and combustion models using different fire brand transport models. We have developed a reduced fire brand transport model to reduce the time step of the calculations. And finally, we have implemented a numerical method to include spotting into a coupled fire atmosphere model. And so what we can conclude is that forecasting spotting faster than real time is achievable. We're able to determine the potential spotting areas, and it can also be of interest for fire management strategies. And so just a couple of perspectives is that, of course, what we would like to do is to increase the number of verification cases. There is a recent paper from the NCAR that have developed a spotting parameterization using a Lagrangian approach, and they have used the Marshall Fire in 2021 Colorado to validate their model. So it will be interesting to compare our model with their case study. There is also room for improvement in the injection mechanism, but that's maybe part of the second PhD of this joint PhD program. And one of the things that we have been working in the last weeks is the actual ignition of spot fires. So here I'm showing kind of an ensemble configuration where we have 4 idealized flat terrains, so pretty simple terrain, with the same input wind flow conditions, but we are just going to parameterize the ignition as a stochastic ignition. And so in green, you see the fire front. So at the beginning, the 4 fire fronts are spreading similarly. This one is creating more spot fires, which is also increasing convection. And for example, in this case, there's also some condensation that is increasing the updraft and making these cases also travel faster than, for example, this one. So we have applied this to the Mount Bolton case, where we use what we call a double threshold stochastic ignition, meaning that to be able to ignite a secondary fire, the density has to be above a certain level, but also below a certain level, because if there is too many fragments, it is likely that we are near the fire front. And so what we have here is 4 different simulations of the same initial conditions, but with different ignitions due to the randomness of the model. So you see that at the beginning there is some spot fires that were generated here. For the moment they are traveling at the same speed towards the south. There is more spot here in green, in blue as well, in pink. At some point we will have a long range spotting here in pink. And of course this is not yet matching the actual spot fires ignition that we observed during the event. It is quite hard to calibrate the ignition model with respect to observations. But we can already have some useful information related, for example, to the maximum burnt area of the fire, and also the minimum one that we could observe if we have ignitions in our model. So we can already have useful information regarding the maximum and the minimum possible burnt area during a fire event. And so, yeah, this is the last part that we have been working on, but of course needs some more adjustment to have it matching the observations. So that was all for me. Thank you for listening. I will take any questions.
Thank you, Alberto, for this nice presentation and very well illustrated.